Question 5. Describe the structure of a step index optical fibre outlining the purpose of the core and the cladding. So they've given us a box here, presumably to draw a diagram. So let's draw a diagram. Should have done this in pencil. There we go. So this material on the outside is the cladding, and this material on the inside is the core. Okay, we have to describe the structure of this and the purpose. So first thing that we need to say is that about refractive indices, for this to work, for the light to totally internally reflect like that, we need the refractive index of this to be less than the core. So the N cladding must be smaller than N core. So that's the refractive index of the cladding is smaller than the refractive index of the core. Right. Outline the purpose of the core and the cladding. So we'll start with the core. The core transmits the light, pulse, using TIR to keep it in the core. So the light bounces backwards and forwards like that using total internal reflection. The cladding. Right, so the purpose of the cladding is, the main purpose of the cladding is to protect the core, to protect the core and to make sure light cannot escape or cross over into other cables. So if you had two cables next door to each other, instead of the light bouncing like that, it might just cross over into that cable there and start bouncing down that one, which wouldn't be very good. So that's why the cladding is there. So it's to protect the core and to make sure the light can't cross over into the next cable. A signal is to be transmitted along a fibre optic cable of length 1,200 meters. The signal consists of a square pulse of white light. Okay, so there's a square pulse of white light. This is transmitted along the centre of the fibre. The maximum and minimum wavelengths of the light are shown in this table. Explain the difference in refractive index results in a change in the pulse of white light by the time it leaves the fibre. Okay, so the bigger the refractive index, the slower the light travels. That's using this equation here. So that's the speed of light in the material, that's the refractive index, so you get a bigger number there and having a slower speed there. So we'll write that down as our first sentence. The greater the refractive index, the slower the wave. Okay, so what does that mean? That means that, well, blue is going to go slower than red. So blue will arrive slower than red. Okay, so that's going to have the effect of stretching the pulse out a bit, like that. And this bit is going to be entirely red. This bit is going to be white as they all arrive together, and then the last bit, the bit that's left over, well, all the red will have already got there, so the last bit is going to be blue. So the first bit to arrive, only the red will get there first because it's going the fastest. The next bit to arrive, everything will arrive, so the red from back here and the blue that started off here will end up meeting each other, and then right at the end the blue will get there. So the blue will arrive slower than the red. This will stretch out the pulse, and the leading section will be more red, and the tailing section will be more blue. The middle will still be white, but that's just because the blue's going slower than the red. Discuss two changes that you can make to reduce the effect that we've described here. Well, the one that we use is we don't use white light. We use lasers which have a single colour. So the first thing to say is to use lasers of a single colour. So a single frequency of light. So that will eliminate the problem because you won't have different refractive indices. It also means that you can send red and blue light down the same signal, the same wire at the same time, and have twice as many signals, because you can send a signal on the red and a signal on the blue using a red laser and a blue laser separately. But we need a second reason. Well, the second reason is essentially to use a shorter cable. So if we use a shorter cable, then this effect won't be so pronounced, because the longer the cable, the more chance the red's got to get ahead and the blue has to lag. Presumably we need to go over the same distance, so we can cut the cable and put a receiver and a booster in the middle. So there's the cable, and you have a big pulse coming out like that. Well, if we send this pulse down here and we have a booster, might be off the page there, and then we send it the rest of the way, then it might have stretched out to there by then, but then we clean it up again and then it'll only stretch to there again. So that's the second method. So we can divide up the journey into shorter lengths using a receiver and cleaning up the signal before retransmitting. So boosting it basically. So shorter distance means that you've got less chance for it to stretch out. So you divide up your distance into two or more smaller segments.